ANAND, Department of Mathematics, Assistant Professor, Satyabama Institute of Science and Technology, deemed to be University, Chennai. Today, I am going to deliver a lecture on Laplace transformation. Laplace transform is defined as L of f of t, where f of t is a real valued function, which is defined as integral 0 to infinity e power minus st f of t into dt. Here you can see the integrand e power minus st f of t dt, integrated t, s is a parameter, it may be real or complex. Now, the question is, Laplace transform exists for all function. So, what are all the function which satisfies these two conditions? F of t must be a piecewise continuous in the interval a comma b, where a is positive, and f of t should be a function of exponential order. Exponential order means as limit t tends to infinity, e power minus st f of t into dt, it should be exist, limit should exist. Now, let us see the Laplace transform of some special functions. First one, Laplace transform of e power a t. Laplace transform of e power a t is 1 upon s minus a, where s minus a is positive. Second one, Laplace transform of e power minus a t. Laplace transform of e power minus a t is 1 upon s plus a. Third one, Laplace transform of sin a t, trigonometric function sin a t is equivalent to a upon s square plus a square. Laplace transform of cos a t. Cos a t is equivalent to s upon s square plus a square. Laplace transform of sin h a t, hyperbolic function, sin h a t is equivalent to a upon s square minus a square. Laplace transform of cos h a t is equivalent to s upon s square minus a square. Laplace transform of t to the power n, t to the power n, that is equivalent to gamma of n plus 1 upon s to the power n plus 1, or it is n factorial upon s to the power n plus 1, where n is an integer, positive integer. Suppose if it is a fractional, then it is gamma of n plus 1 upon n plus 1. Some problems based on Laplace transformation. Laplace transform of e power 2t, exponential function, that is equivalent to, using the formula, 1 upon s minus 2. We have seen Laplace transform of e power a t is equivalent to 1 upon s minus a. Similarly, Laplace transform of e power minus 3t is equivalent to 1 upon s plus 3. Laplace transform of sin 4t is equivalent to a upon, a is 4 here, 4 upon s square plus 4 square, that is 16. So, it can be rewritten as 4 upon a square plus 16. Laplace transform of cos 2t is equivalent to s upon s square plus 2 square, it is 4. So, Laplace transform of sin h t, Laplace transform of sin h t is equivalent to a is 1 here, 1 upon s square minus a square. Laplace transform of cos h 2t, that is equivalent to s upon s square minus a square. A is 2 here, therefore, s upon s square minus 2 square. Now, Laplace transform of t power n we know. Laplace transform of t power n is equal to n factorial upon s to the power n plus 1. I said when n is an positive integer, then this holds n factorial upon s to the power n plus 1. Laplace transform of, let us say, t. What is the power here? The power is 1. Therefore, 1 factorial upon s to the power 1 plus 1, it is 1 upon s square. Laplace transform of t is 1 upon s square. Laplace transform of t square, t is a whole number, positive integer. Therefore, it is 2 factorial upon s to the power 2 plus 1, it is 2 upon s cube. Laplace transform of, let us say, t to the power of, that means Laplace transform of root t. This can be rewritten as Laplace transform of t to the power of. So, it is a fraction. Therefore, we know the formula gamma of n plus 1 equivalent to s to the power n plus 1. So, it is gamma of n is of plus 1 upon s to the power of plus 1. We know the formula gamma of n plus 1 is equivalent to n into gamma of n. Gamma of a function, gamma of n plus 1 is equal to n into gamma of n. By using this formula, this can be rewritten as half into gamma of upon s to the power 1 plus half is 1 and half, that is 3 over 2. So, gamma of half value we know, gamma of half value it is equal to root pi. Gamma of half value is equal to root pi. So, that is equivalent to 1 upon 2 into root pi upon s to the power 3 over 2. 3 over 2. Suppose if you want Laplace transform of 1 over root t, that is equivalent to Laplace transform of t to the power minus of. So, that is equivalent to, it is a fraction, therefore, it can be written as gamma of minus of plus 1 upon s to the power minus of plus 1. So, minus of plus 1 is gamma of half, this one half upon s to the power 1 over 2. Gamma of half value equal to root pi. So, it can be written as root pi upon root s, that is equal to, it can be brought under same roof, pi over s, under root pi over s. Let us see some properties. Laplace transform of linearity property. Laplace transform some c1 into f1 of t plus or minus c2 into f2 of t, that is equivalent to c1 into Laplace transform of f1 of t plus or minus c2, where c1 and c2 are constants, Laplace transform of f2 of t. And one more note, the very basic definition of Laplace transform, we know that L of f of t, it can also be denoted by capital F of s. So, when you take Laplace transform of f of t, where f of t is a function defined on the interval on the real line, it will be converted into f of s, where s is a parameter. So, it can also be denoted by capital F of s. Property number 1, shifting property, Laplace transform of e power a t into f of t. So, f of t is multiplied by the exponential function, then the resultant is L of f of t replacing s by the parameter s by s minus a, or it can also be written as capital F of s minus a. If it is e power minus a t, L of e power minus a t into f of t, then it can be written as Laplace transform of f of t replacing s by s plus a, that is same as saying that f of s plus a. Using this notation, L of f of t is equivalent to denoted by capital F of s. This property is called shifting property. The second property is change of scale property. Change of scale property, Laplace transform of f of a t. Laplace transform f of a t, where a is a constant, that is equivalent to 1 upon a into f of s upon a. 1 upon a into capital F of s upon a. The third thing, Laplace transform of t power n into f of t. Laplace transform of t power n into f of t, that is equivalent to minus 1 to the power n times you differentiate with respect to the parameter into L of f of t. If you want, you can replace this L of f of t by f of s, that is nothing but the Laplace transform of f of t. The fourth one, Laplace transform of f of t upon t. F of t upon t. So, that is equal to integral s to infinity L of f of t into ds. What is this L of f of t? It can also be replaced by capital F of s into ds. So, you have to integrate with respect to the parameter s, lower limit is the variable parameter s to infinity. This is exist provided the limit of this one should exist, provided as limit t tends to 0, f of t upon t should exist, then only it is valid. So, let us see some problems based on these properties and theorem. Find Laplace transform of e power t into sin 3t. This is of the form e power a t into f of t. So, we can make use of shifting theorem that says, first find out Laplace transform of sin 3t. Whatever answer you are getting, replacing the parameter s by s minus 1, because a is 1 here. So, that is equal to Laplace transform of sin 3t is 3 upon s square plus 3 square, replacing s by s minus 1. So, that is equivalent to 3 upon s minus 1 the whole square plus 3 square, it is 9. This is the answer. If you want, you can further simplify, expand it and further simplify. The second one, find the Laplace transform of e to the power minus 2t into cos t. It is of the form e power minus at into f of t, Laplace transform of e power minus at f of t. That is equivalent to Laplace transform of cos t, replacing the parameter s by s plus 2, because a is minus 2. That is equivalent to Laplace transform of cos t is s upon s square plus a square, a is 1 here, replacing s by s plus 2. We get s plus 2 upon s plus 2 the whole square plus 1 square. Let us find Laplace transform of t into e power 2t. This problem, look at this function t into e power 2t. Either we can apply the first shifting theorem, or we can solve this problem by using the theorem called Laplace transform of t into f of t, t power n into f of t, general form. So, that is equal to, if you use that formula, we get minus 1 to the power 1, because t power 1 is there, n is 1, into Laplace transform d upon ds of Laplace transform of e power 2t, e power 2t. So, that is equal to minus 1 into d upon ds of Laplace transform of e power 2t, it is 2 over s minus 2, 2 upon s minus 2, it is in quotient form, u by v rule. If we use that, then we get minus 1 into differential of this denominator square, denominator into differential of the numerator. Differential of the constant with respect to x is going to be 0, minus numerator, it is 2, into differential of the denominator. Differential of the denominator, ds upon ds is going to be 1, differential of a constant is 0. So, it is 2 into 1. So, on simplification, we get minus 1 into s, this is 0, cancel, minus 2 upon s minus 2 the whole square. So, minus into minus going to be plus. So, on simplification, it is 2 over s minus 2 the whole square. The same answer you will be getting by using first shifting theorem also. Now, let us look at Laplace transform of 1 minus e power t upon t. You can see here, it is of the form f of t upon t. F of t upon t, we can find the Laplace transform of this, provided the limit of this bracket quantity should exist. That means what? As limit t tends to 0, e power 0 is going to be 1, 1 minus 1 it is 0 upon 0, it is 0 upon 0 form. We can make use of L'Hopital's rule, I mean L'Hospital rule, and then L'Hospital rule says differentiate numerator separately, differentiate denominator separately, and then apply the limit. So, when you do so, we get a finite value, that means limit exists, therefore, we can write the Laplace transform, this one is equivalent to integral s to infinity Laplace transform of the numerator, L of the numerator 1 minus e power t into ds, Again look at this integrand, Laplace transform 1 minus e power t. So, that is equivalent to integral s to infinity Laplace transform of 1, it is 1 upon s. Laplace transform 1, it is 1 upon s, minus Laplace transform of e power t, 1 upon s minus 1 into ds. Integral s to infinity, Laplace transform 1 is 1 upon s, Laplace transform of e power t is 1 upon s minus 1. We know that integral of ds upon s is log s. Similarly, integral of ds upon s minus 1 is log of s minus 1. So, that is equivalent to log s minus log of s minus 1 limit s to infinity. It is of the form log a minus log b. It can be written as log a upon b. That is equivalent to log a upon b, s upon s minus 1 limit, lower limit is s, upper limit is infinity. Okay. So, take the parameter s outside. So, if we take the parameter s outside, s in the numerator, s comes outside. So, the denominator becomes 1 minus 1 upon s. So, that is equivalent to s get cancelled, log of, if you take s numerator common, this becomes 1, s 1 minus 1 upon s, limit s to infinity. So, s get cancelled. Okay. Now, substitute upper limit minus lower limit. If you substitute the upper limit here, 1 upon infinity is 0. So, log 1 remains, log 1 upper limit minus lower limit is s. So, yes, that is it. So, if we take LCM, what will happen? S minus 1 over s reciprocated, it is log of s minus 1 upon s. So, s upon s minus 1. We know that log 1 value 0, 0 cancel it out. So, that is equal to minus log of s upon s minus 1. If you multiply by minus sign, log a by b become log b by a. So, that is equivalent to log of b upon a. B upon a is what? S minus 1 upon s. So, this is a Laplace transform of 1 minus e power t upon t. Laplace transform of this one exists, solving some problems using Laplace transformation. Look at this integral, I is equivalent to integral 0 to infinity e power minus x square into dx. Let us put x square equivalent to t, differentiating on both sides. So, we get 2x into dx is equivalent to dt. What are the limits? So, we are converting into the variable x into new variable t. When x is 0, t is also 0. When x is infinity, t is infinity. So, this integral becomes I is equivalent to integral 0 to infinity e power minus x square, that is e power minus t dx. dx is what? dt upon 2 into x, dt upon 2x, that is equal to integral 0 to infinity. By the property of definite integral, what constant can be taken outside? 1 over 2 into e power minus t x. What is that x? Root t. So, root t can be taken to the numerator. So, t to the power minus half into dt, right? dt. Now, as we all know, the gamma function, gamma of n is equivalent to integral 0 to infinity e power minus x into x to the power n minus 1 into dx, a gamma function. Just compare. So, n minus 1 is equivalent to minus half, n minus 1 is equal to, here n minus 1 is equivalent to minus half. So, what is that n? Minus half plus 1. So, n is equivalent to 1 minus half is half. So, this can be written as 1 over 2 into this whole term, this can be written as gamma of half. What is gamma of half value? Is root pi, it is root pi upon 2. Okay. Therefore, using Laplace transform also we can solve. This is a direct method. If you know, provided if you know this gamma function, then we can find the answer root pi upon 2. Suppose if you are good enough in Laplace transform and all, just compare Laplace transform of f of t. integral 0 to infinity e power minus st into f of t dt. F of t dt. Now compare here e power minus s into t. Of course, here the parameter s is equal to 1 in that sense. F of t. What is f of t? T power minus half. So that is same as saying that Laplace transform of t power minus half. We have already proved Laplace transform of t power minus half is something. Convolution definition. The convolution of two functions. The convolution of two functions. Let us say f of t convolutes with g of t. It is defined as integral 0 to t f of u into g of t minus u into d. Into d. The convolution of two functions. 0 to t f of g of t minus u into d. Actually, it is a superposition of two waves f of t and g of t at t is equal to u. Okay. And one more thing, Laplace transform of convolution of two functions. Let us say f of t convolutes with g of t. That is equal to product of their Laplace transform. So, one of the important property, product of the Laplace transform. So, it is L of f of t into L of g of t. So, this can also be written as f of s into g of s. The very beginning I explained a Laplace transform L of f of t can also be written as f of s, where s is a parameter, t is a variable. Okay. So, Laplace transform of convolution of two functions is equivalent to product of their Laplace transform. Some important theorems. Laplace transform of f prime of t, that is equal to s into L of f of t minus f of 0. Laplace transform of first order derivative of a function equal to s into L of f of t minus f of 0. Similarly, Laplace transform of f double dash of t is equivalent to s square into L of f of t minus s into f of 0 minus f prime of 0. So, like this we can generalize the case for Laplace transform of f n of t. Now, you take Laplace transform on both sides. Before we taking Laplace transform, look at this integrand. This is of the form convolution type, integral 0 to t f of u g of t minus u into du. Therefore, this can be rewritten as y prime of t y of t convolutes with cos t. So, this particular part using the convolution definition. Now, you take Laplace transform on either side. Taking Laplace transform on both sides. So, this becomes L of y prime of t is equivalent to Laplace transform of y of t convolutes with cos t. We know Laplace transform y prime of t. Laplace transform y prime of t, where y of t is a function, then we will get as Laplace transform of y of t minus y of 0. That is equivalent to Laplace transform of convolution of two functions. Convolution theorem says Laplace transform of convolution of two functions is equivalent to product of their Laplace transform. By using that convolution theorem, this can be written as L of y of t into L of cos t. So, this one by convolution theorem. Look at the initial condition, y of 0 equivalent to 1. Let's substitute here s into L of y of t minus 1, it is given L of y of t into Laplace transform of cos t, s upon s square plus 1. Okay. So, we bring that to the other side, L of y of t, L of y of t, we get s minus s upon s square plus 1 into L of y of t. Push this one to other side, it is equivalent to 1. Okay. You take LCM, this becomes s into s square plus 1 minus s upon s square plus 1 into L of y of t is equal to 1. So, when you simplify, this becomes s cube plus s minus s. So, plus s minus s get cancelled. We get s cube upon s square plus 1 into L of y of t equal to 1. We want y of t, that is our aim. For solving this function, we want y of t alone. So, keeping this alone here at one side, push this to other side. So, what happens? L of y of t is equal to 1 upon s cube upon s square plus 1. So, reciprocate this. So, this will become L of y of t is equal to s square plus 1 upon s cube. 1 upon s, the square get cancelled by s, plus 1 upon s cube. So, there are two terms, I have stated it. Our aim is to find y of t. So, L of y of t is here, taking inverse Laplace transform on both sides. Inverse Laplace transform on both sides. We get L inverse of L identity. So, this becomes y of t equal to L inverse of 1 upon s plus L inverse of 1 upon s cube. We know that Laplace transform of 1 equal to 1 over s. So, if we take inverse Laplace transform, L inverse of 1 over s is equivalent to 1. Okay? Plus, it is not in the standard form. Standard form, I mean, we know the Laplace transform of t square is equivalent to 2 factorial upon s to the power 2 plus 1, that is same as 2 upon s cube. But what is missing here? 2. So, in order to bring this one into the standard form, multiply and divided by 2. So, multiply and divided by 2, this becomes L inverse of 2 factorial, it is 2 upon s cube. Now, look at this one, it is of the form 2 factorial upon s cube. We know that Laplace transform of t square is 2 factorial upon s cube. So, when you take inverse Laplace transform, L inverse of 2 upon s cube is t square. So, that is equivalent to 1 plus 1 over 2 into t square. So, that is the solution of this differential integral equation with the initial condition y of 0 equivalent to 1. Now, I know I did not touch this inverse Laplace transform. In the next lecture, we will see some inverse Laplace transform equations, standard equations, and then applications of inverse Laplace transform, and also how to solve some special functions using Laplace transform like Bessel's function, Legendre function, some special function like that using Laplace transform. Thank you.